and welcome to the Diabatix Summer Series. I'm Reshmaa Selvakumar and I will be the host for your webinar today. I'm an application engineer at Diabatix and I usually serve as an interface between our users and the software, so I help them with providing support, giving them training, etc. This is the third installment in the Diabatix Summer Series, which is a short series of webinars that will help you familiarize yourself with the platform's different features and also, just help you up and running in using the ColdStream platform. Like I just mentioned, the Diabatix Summer Series is a very short series of webinars that we have organized to help you understand the platform more. The last two webinars were conducted by my colleague Hertian Paulus, and he focused on topics that involved simulations on the platform as well as post-processing on the platform. In today's webinar, I will be setting up a design case or an optimization case on the platform, and we will look at the post-process results as well. And for this subject or this topic, I have chosen to work with an eMachine cooling jacket. So we would look at how to create or design this high-performant cooling jackets for eMachines or electric motors. In 2 weeks from now, on the 27th of August, there will be another webinar by Dr. Van der Beek, and she will be talking about how to apply boundary conditions on the platform. Let's take a look at the case setup for this cooling jacket. This is the start of the case that we will be looking at setting up on the platform today. This would be what you see here would be the heatsink or the cover of the cooling jacket. This is just the solid region, and inside this cover you would typically place your eMachine or your electric motor. We haven't modeled the entire electric motor, even though you can, because from our perspective it does feel like an overkill, because instead what you can do as a replacement of putting the entire or modeling the entire electric motor is create a heated wall boundary in the inside of this cover where your electric motor will sit. I'll talk about that a little bit more in detail on the next slide, but for now, when you look at just the solid region, this is the material that we will be using for this solid region. It's an aluminum alloy of 6061 with a thermal conductivity of 180 watt per meter Kelvin. Other than the solid properties, of course, like I just mentioned, the important part of the solid region would be the heated wall, which is inside this cooling jacket cover, and this is typically the wall or the surface that would be directly in contact with the outer region in terms of the heating power. And the heating power itself is around 700 watts. That's the maximum heating power for this heated wall, and that's what we will take into consideration in our case setup as well. What you see here now is the fluid region, and the fluid region is basically the region where your coolant will flow in the cooling jacket, and this you can model in your CAD tool. So basically this is where your inlet is, and your fluid or your coolant is expected to flow all around this region, and then this part over here would be your outlet connection. And the coolant itself in this case is a water glycol mixture of 90% water and about 10% glycol. And you also have some of the boundary conditions mentioned over here. So the inlet temperature of the fluid is around 60 degrees Celsius. And you also have the volumetric flow rate that's mentioned here. It's about 6 to 10 to the power minus 5 meter cube per second. And you also have a constant pressure outlet for this case. Let's look at the design region next on the next slide. Design region. So typically the design region would be a sub-region in the fluid region. You would have seen that with various other cases and in our different webinars and demos, and it's the same in this case as well. Your design space or your design region is basically the entire region where the fluid would flow, but minus the inlet and the outlet. So it's really you're restricting the optimizer or the software to place your cooling channels in this region and draw these organic or cooling channels only in this space and nowhere else. That's why a design space is very important, and that's also why you cannot start a design case on the ColdStream platform without defining a proper design space. In terms of manufacturing, we're going to choose 3D printing. The minimum feature size or tool size is about 1 mm, and we can incorporate this in the manufacturing settings of the platform. And we can just choose the manufacturing type and the manufacturing setting during our case setup. The next step, of course, is our optimization target. The optimization target that we have right now is to minimize temperature. We also have a pressure drop constraint of about 5.8 kilopascal. Now, this is an important concept that we need to understand, which is the difference between an objective and a constraint. When you look at the optimization target over here, I have the first point, which is to minimize temperature, and minimizing the temperature as a whole would be an objective, or it's something that you're looking to optimize for the design case. The second thing that you have over here is a pressure loss that this case cannot exceed. So it's a maximum pressure loss with a defined number of 5.8 kilopascal, and that would be a constraint. And that's a major difference that we always need to keep in mind when it comes to setting an objective and a constraint. It's important to know that and incorporate that in your cases as well. Now let's go to the platform and start setting up this case. Now let's start setting up the case on the platform. I'll begin with adding a case under the cooling jacket project on my account. Of course, if it's more easier for you, then you can also create a project under a name before you start adding the case in the particular project. I'm going to call it temperature minimization, and then I have to choose a case type. Here we have an option of choosing a case type between a design or a simulation, and since it's an optimization case where we would like for these cooling channels to be drawn automatically by the software, then we choose a design case. A simulation case usually is just a CFD simulation. Now we start setup, and then we upload the step file. Yeah, so we choose the step file that we would like to input for this case, and then we just populate the case with this particular step file. For the case setup, I typically have a 5-step process. We start with uploading the geometry on the platform, which is what we're doing right now by populating the case. The second would be to apply all the boundary conditions. The third step would be to include manufacturing settings and as part of your desired region. The last step that we would have would be to include your optimization targets and constraints, and the last step would be validate your geometry and submit the case. All right. Let's set up this case now. So the geometry, as you can see, has been uploaded. And as you can see, this would be my solid region. And that's basically region 0. So if I hide region 1, you see that this is basically the cover of the electric motor cooling jacket. Let's start with including the boundary conditions for this region. So region type, we choose solid. Let's give it a name, call it cover, and then select a material. So we're just going to select the aluminum alloy that we've chosen for this case from the material library. And then for this region, there were no other additional physical properties that played a role, so we don't have to include them. The next is the boundary itself, which is basically the heated wall of the in place of the electric motor that would typically sit inside this cooling jacket. So we just say heated wall and say call it a heat source, and then the heating power we go with is 700 watts. Now the solid region is complete, so let's do the fluid region. So if I hide the solid region, then you see what we have right now is basically the fluid region with an inlet over here and an outlet over here, and we can set up this case as well. Region type, fluid, and then we give it a name as fluid as well. Then we select a material for water glycol mixture of 90-10. So let's choose water glycol 90-10 as our material. And then we don't have any buoyancy related settings or radiation related settings, so we don't have to activate them. And in terms of the turbulence model, I would like to keep it at k omega SST. Now, if we click on the fluid region, there is a sub-region inside it, which is our design region, and then 2 other boundaries. Let's start with boundary 0, which is basically our inlet over here. So let's choose fixed flow rate inlet. Of course, you can choose other types of inlets as well, but this is what applies to this case. And then we can rename this as inlet, and we have to set the temperature. The inlet temperature for this case is around 333.15 Kelvin, and then the volumetric flow rate is 6 into 10 to the power minus 5. Small mistake there. So we've included the inlet temperature as well as the mass flow rate. So the inlet boundary conditions are set. Let's move to boundary 1, which is basically our outlet. So for this, we will choose a pressure outlet. Give it a name as outlet and set a constant pressure of 0 Pascal. Moving on to the sub-region, which is basically our design region. The type of sub-region, it's a design region. Give it a name, design. Before we choose a material, I quickly want to show you how the design region looks like. And it's basically the fluid region minus the inlet and outlet boundaries. So as you can see, or like connections, sorry. So as you can see here, it is the same region where the fluid will flow, and this is the area where we want the cooling channels to be placed. Of course, we don't want them to be placed where the inlet and outlet is, and hence that has been removed, but the rest of it does apply to the design region. Let's choose the material. I'm going for the same material as our solid, So aluminum alloy 6061 annealed. And then I would choose the manufacturing type, which is 3D printing, and then select the manufacturing settings of 1 mm. And that's it. So we've basically set up our manufacturing settings as well as our boundary conditions. Our next step is, of course, to include our objectives and constraints. Let's start with our constraints, so which is the pressure loss constraint, and we would apply that on the inlet. So we just choose inlet, and then at the bottom here we click on add target, and then we choose pressure loss. Be careful, a pressure loss minimization is an objective. Like I said, a pressure loss, on the other hand, lets you define the maximum pressure loss constraint that you would like. In this case, it was about 5.8 kilopascal, and then we've set the constraint on the inlet, and now we have to set the objective, and that would be on the heat source, because our objective or target is to have a temperature minimization. So we click on add target again, choose temperature minimization from the list, and then that has been set as well. That's it. So at this point we have finished our case setup. So we've uploaded the geometry, included our boundary conditions, our manufacturing settings, as well as our optimization targets and constraints. So we just validate the geometry and submit the case. Now we can choose to submit the case either as a detailed design or a conceptual design. A conceptual design is a first estimation of how the results would be or how it would look like, and a detailed design is more accurate, and it gives you a high resolution result with manufacturability accounted for. And we can also choose the number of credits that we would like to apply, and this in turn would affect the runtime for these cases. So you can choose what you want. I'm going to run a detailed case for 85 credits now, and I'm just going to click on OK. So now that we have this case already running, I'd also like to show you some results related to this case. And I've already run this case previously on the platform, so we can already look at the finished results for the same case setup, and that's what we will be looking at right now. So this is the case that I've previously run, and I have the finished results for. As you can see here, you already have on the case summary some of the preliminary results, like temperature, pressure, Y-class imbalances, etc. Our main focus was the temperature minimization, so let's take a look at that quickly. You see here, you can see the temperatures in Kelvin, but you could also change the units and take a look at these temperatures as well. So other than this, you can also download the results as well as the design itself on this tab. So when you download the results, you can basically do the post-processing on your internal post-processing tool if you want to, and with downloading the design, you will have another step file of the design itself. So the temperatures, as we see here, our inlet temperature that we set was 60 degrees Celsius or 303.15 Kelvin. And when you look at the maximum temperature at the heated wall, it's only 335. So it's only a 2 Kelvin rise that we see, and it's much lower than what would be expected in cases like this. So it has gone through to give you an optimum temperature. So what we can do quickly is visualize these results on the 3D results tab. So we can take a look at some of the results, the post-process results. All right, let's start first with looking at the design itself and how that looks. So I'm just going to quickly visualize that. I'm going to hide all these external, um, all these other plots that I don't want to see, and then we can take a quick look at the design. So this is how the design looks. It's of course going to be 3D printed, and you can click on this, and you can also choose for it to be in a solid color, and quickly visualize the design as such. It would also be interesting, of course, to look at the streamlines, but for now I would quickly take a screenshot of this to give an idea of how the design looks like. So I just click on the take screenshot button, call it design.png, transparent background, and then download it. Let's look at the streamlines now. You can of course color the streamlines as well with any of the parameters that you want to. So say I want to color with velocity, you see automatically that there is a range of the parameter that you've chosen, and you can quickly see the streamlines accordingly. So you can do the same with different temperatures. You can also take a look at, for example, the solid surface itself, and how the heated wall and solid surface itself, and how that looks as well. So we could try and look at that quickly. So if I were to color that with the temperature input, then you'll kind of see where you have where you have the maximum temperature. Again, I do want to point out that the range of the parameters are also quite important, and you can also set a different range to take a look at this value, and then you can take a look at the heat input, or the temperature plot as we call it. So there is a certain amount of post-processing that you can do on the platform itself, but otherwise you can always also just download the results and do the post-processing on your post-processing tool as well. With that, we come to a conclusion of this Diabatix webinar. In 2 weeks, we will have another webinar in this series, which will be our last installment, and that will be by my colleague Dr. Vanderbeck, and she will give the webinar about applying boundary conditions on the platform. If you want to see any of the previous webinars or rewatch anything, you can still find that on our webinars page on our website. So you can still take a look at the you can still rewatch the webinars, because there will be recordings of the webinar uploaded there, along with the different reports for each of the different webinars that were conducted over the last few months. I hope everything was clear, and I hope you learned how to use the platform as well. Thank you for joining me today. I do see there are quite a few questions, but unfortunately we are running out of time, and I will not be able to answer them right now, but I will reach out to you, to everyone who's asked questions, and I will answer you over the course of the next week with the answers to your questions. Thank you for joining me today. I hope you enjoyed the webinar and learned something from it. If you have any questions, or want to know more information, you can always contact us via the website, or you can also reach out to me directly, and I will be able to assist you. Thank you. Have a nice day.